Good morning, good afternoon, and good evening, folks, wherever you're joining from us today. Welcome to today's webinar on Accelerate Your Valve Design Process using Autonomous Valve CFD. I am Manish Kamath, your friendly technical sales engineer here at simulationHub. I am pleased to announce our expert speaker for today, Mr. Praveen Kumar. Praveen is a product manager here at simulationHub and has more than 15 years of experience in computational fluid dynamics and applying CFD to optimize and evaluate different types of thermal and fluid design systems. But before we start, a few housekeeping items. First of all, we'll be recording this webinar and it will be available to you for your future references on our YouTube channel, as well as on simulationHub's website. So please keep your mics on mute during the presentation to avoid any background noises. If you have any burning questions during the presentation, feel free to toss them in the chat box. We'll be answering them all at the end during the Q&A session. So without any further ado, let me hand over the mic to Praveen. Praveen, take it away.
Thanks, Manish. That was a good, short and crisp introduction. Hello, everyone. Excited to connect with you all in this platform. So this is the agenda for today's webinar. We have a mixed set of audience. Some might be new to this domain and some might be expert. So I thought of covering or starting from the basics to set the platform, to bring everyone on the same page. Then we jump into the core topic of today's webinar, which is the Autonomous Valve CFD, how we use it to evaluate the valve performance of valve coefficient. So pardon me if few things sound obvious to you guys. So yeah. So first we'll start with valves and introduce you to two valve coefficients and the methodology to evaluate those valve coefficients, and introduction to the app Autonomous Valve CFD and the app demo, and we'll end it with the Q&A session. So live interactions and things. I'm looking forward for that. Okay. So what are valves? So these are devices that is a part of a loop or a system that controls certain parameters in the process. So parameter could be flow or fluid flow, pressure or temperature. Depending on the application, it is classified into different categories. For example, if it blocks or isolates a fluid, then it is called on-off valve. So if it is used for controlling or modulate or throttle, it is called control valves. And mixing fluids. And there are certain valves for backflow prevention and pressure relief devices as well. So on the right side is just an illustration of how a valve can control these parameters. It is done by varying the flow area. So by bringing some restrictions in the flow area, the pressure and velocity changes, and different designs, with the help of different designs, we can control exactly the way we want to control the parameter. Okay, so there are different types of valves, largely classified based on the motion. So if it is rotary motion, if the moving component or trim is rotating to control the flow, then it is to on and off or control. So it is called rotary valves, and one, if it moves linear direction, then it's called linear valves. So globe valve is a linear type valve, and butterfly valve or ball valve can be termed as rotary valve. So there are different types of valves. And the valve application extends from very large oil and gas industry to pharmaceutical or food and beverages, and everywhere. You name any industry, you cannot skip the importance or criticality of a valve. So for power generation, it's very critical to control the performance as well as the safety, to maintain the safety of the power plant. So valves play an important role in each and every industry. Okay, you might be familiar with this kind of tables being published in the valve manufacturer's catalog or data sheet So what is this? This is a way to evaluate. This is kind of in layman's term, it's a score of design score of a valve. So kind of flow performance score of a valve. So this is called CV, valve flow coefficient. So this number indicates some certain thing. Okay. So on the column wise, there are the valve opening, either angle or the percentage of travel, and on the rows it is the valve sizes, and this is the numbers which are CV data. So CV is the capacity of a valve for a given pressure drop. So how much a valve can deliver, how much flow, volumetric flow it can deliver for a given pressure drop. So that is CV. So the official definition comes something like this: the volume of water that will flow through a valve per minute with a pressure drop of 1 psi across the valve. So CV is calculated for a valve at each angle of opening or percentage of opening using this method. So once we know the pressure drop and the flow rate, then we can calculate the CV. So for once we calculate the CV for every angle of opening or percentage, then we can plot the continuous CV curve. So this tells us how the valve will behave going from fully closed to fully open position. So the CV curve shape can vary depending on the valve characteristics. So it could be quick opening or equal percentage or linear curve, or that some modifications with the three major types. So what is the importance of CV? Why we need to know the CV data of a valve? So it helps us to compare flow capacities of two different valves from two different manufacturers, or within the same manufacturer, if you want to size or select a particular valve which is of right size. Okay. So this is the importance of CV. If you have improperly sized or oversized or undersized your valve, then it can cause a lot of damage to the valve. It can induce cavitation as well, because if you oversize your valve, most of the time, operating time ends up in your valve being operating in a lower angle of opening or percentage of. So there, the possibility of cavitation rises. So proper sizing of valve is important, and CV helps. Accurate CV values is very critical to assist your end user to select the right size for the application. Okay, so here I'm introducing another parameter, which is hydrodynamic torque, which is nothing but the turning moment created because of the fluid forces, difference in fluid forces on the upstream and downstream side around the rotating ball. So it helps in actuator sizing and selection. So the coefficient associated with hydrodynamic torque is coefficient of hydrodynamic torque, which is CDT. So once you know the torque and pressure drop, you can calculate CDT. A typical CDT curve looks something like this. Okay, now we have necessary basic fundamentals covered. So we have introduced CV and CDT. Now, how do we get the CV and CDT? So there are labs, certified labs, which performs this flow loop testing. Labs like Utah Laboratory in USA and FCRA in India. So these labs perform flow loop tests based on a regulation set by ANSI ISA standards 75.02.01. So these standards set regulations about how to conduct the flow loop test and extract your CV, estimate your CV, evaluate your CV for the given valve design. So this is about CV, and the procedure is kind of slightly different. There are a different standard, AWWA M49 standard, which provides the regulations about how to conduct experiment and how to extract CDT for a valve. But the flow setup of the CDT is also same as that of CV. For example, where you have to place your probes or monitors, pressure taps. So it should be 2 times the diameter of the valve upstream and 6 times the diameter of the valve downstream. So these are the formulas with which you can calculate the CVT from flow loop test experimentally. Okay. So now, who uses this? Things. So there are 2 use cases. I'll talk about this first. There is something called legacy design CV data generation. So what happens is, few manufacturers have manufactured the valve. The valve is physically present, but the CV data is not generated or it's missing. Okay, it's not. It's based on some old analytical or based on the experience and some analytical calculations. It was there. They wanted to upgrade or update the CV data table. So what they do is some unfortunately, few manufacturers might go for picking one size out of the whole series, perform a flow loop test, extract the CV, and for the rest of the sizes, they simply use some scale ratio and generate CV data, the entire CV table. Of course, it may not be the case with every manufacturer, but there are a few places where they tend to do this because of some constraint, the time and cost involved in actual conducting an actual flow loop test and extracting the data. Okay. So this method is not recommended. We have already discussed the impact of less accurate CV end up costing the project itself in some cases. So this method is not recommended. And the other use case will address how to resolve this issue. Okay. So another use case of CV is like a new product development. So here the product doesn't exist. We have a design requirement, a target CV, which we need to achieve. So the designer designs a valve, send it for manufacturing a prototype, and transport that prototype to a remote location or somewhere else in the country or state. So where the flow loop test facility is available. So they perform the flow loop test and provide you with CV and CDT flow performance report. So what this report has is CV and CDT values. Okay. So this process takes weeks to months, depending on the load of the facility and depending on a lot of manufacturing time and everything involved. So it goes in months. But the problem here is it doesn't as it sounds, it doesn't it is not simple as it's okay. So once you get the response for your first design, let's say the report says your CV doesn't meet your target CV. So now you have to do some design modifications and repeat the entire process again until you match your target CV. So there will be multiple design iterations and it doesn't end there. The real problem is on what basis the designer can modify. They know what is the CV. They know the pressure drops, pressure values at 2D and 6D probe tap positions. That's it. What is the problem? Where do I, play with the design so that how can I improve my design? How can I improve flow performance? Which design element will bring my CV closer to my target or requirement CV, right? So that is not known. So this is a drawback of this flow loop test. Yes. So I'm listing out the challenges in flow loop test. So one is, resource limitations to be there. Not all flow loop test is equipped with setup of testing large diameter valves, and the design changes. Each and every design changes will repeat the cost and time involved, and the limited flow insights. As I discussed, you do not know where the flow separation is, what is costing you flow separation, what is costing you the high pressure drop. How can I fix the design? So that information of flow or flow insight is limited in this. Okay, so what are the alternate methods? So as we already discussed, like analytical method is an alternate for flow loop, but the accuracy is very less. It's not recommended at all. Although the time and cost might look attractive, but it's not recommended. So the other option is the numerical method or the CFD. So the accuracy is very pretty close to the flow loop test, but the time and cost is involved is might be better than flow loop test, but it's kind of it's considerable. And the skill set required to perform CFD simulations, use a CFD tool, and that is still high. Still a nightmare for a designer for himself to extract a CV from a CFD simulation. So we'll again address this issue for the slides. Let me go ahead. So here I'm putting a picture about what it takes, or what is the CFD process of a conventional CFD approach. So it starts with the geometry, and there is something called fluid volume extraction or CAD cleanup and fluid volume extraction. Then the fluid volume is discretized with hexahedral or tetrahedral cells, what we call it as meshing. And we do some solver setup, select some turbulence model, write appropriate turbulence model for the physics which we are solving, appropriate numerical schemes. And then the simulation is performed on a high performance computing setup. So it takes, a HPC high performance machine to perform this CFD simulations. And then you get the results in 3D, like the colorful results, where you get more insights. So this is where I was saying, you get detailed insights. So what does this blue indicates? This is flow separation area. So how do I, improve my design? So all those insights can be interpreted from this result. And then you get the qualitative and the quantitative results. But the problem is each and every step needs a different technical expertise. Okay. So once the design is submitted by the design engineer, the CAD repairing knowledge is required, which physics-based mesh refinement is required, and which a suitable solver for the physics which we are solving, and then large computational power in-house is required. And then domain understanding and CFD expertise is required to interpret the results and generate a meaningful report. Okay, that can be useful. Okay. So these are the challenges. So it demands CFD knowledge and expertise, and it demands HPC hardware, high power computing machines in-house, and the CFD software, costs you like heavy licensing costs. When I say licensing costs, there are some hidden elements. So there are different options like parallel licensing, perpetual licensing, and then annual maintenance cost. So the list goes on. So okay. So these are the challenges we discussed. What if I tell you, what if this CFD processes are automated and then performed autonomously without need of any expertise, technical expertise? What if I say a method, a technology which will remove the need for in-house HPC machines? The simulations can be performed on the cloud platform. So what if I said the meaningful reports and result interpretations can be automated and autonomously shared with the users? It'll be great, right? So with this vision, simulationHub team has developed a platform which is to develop cloud-based CFD simulation apps for designers, which is built on different latest technologies like AWS, Amazon Web Services, OpenFOAM Solver, and Autodesk Forge for 3D visualization, CAD and result visualizations. So on this platform, we have built Autonomous Valve CFD, AVC, specialized for valve CFD simulations. So this is kind of, you can consider it as a virtual flow loop test because it follows the same standards and guidelines provided in the ISA standard as good as, the flow loop test. So it provides CV, KV, and CDT and head loss coefficients and other coefficients as well. So this app supports all the valve types I have listed out here. So majorly control valves and isolation valves, rotary motion and linear motion. So ball valve, all ball valve types like full port, reduced port, V ports, segmented ball valve, double offset, concentric, triple offset, and globe valve types. So all these valves are supported in the app. So what is required? So it is a web application. So when I say web application, it doesn't need, it doesn't use your local machine for simulations, computations. So you don't have to install the app on your machine. So you can open your browser, just directly log into the app and start using it. So all you need is a web browser like Chrome or a good internet connection and any machine to access the application. So it works on PCs, mobiles, and tabs, laptops. So that's it. And the workflow is simple. In a short time, like we will go through a working demonstration of the app. There it will be much clearer, but I'll just go through slightly. I'll explain you in a brief. So it starts with the geometry, uploading the geometry of the valve, specifying the flow direction, and submitting it for solve. So the simulations will be performed on the cloud, and the results can be viewed on the browser. So it's as simple as this. So what are the inputs required for the app? So the CAD geometry which you are going to upload, and you have to specify what are your trim components or moving parts, and what is the flow direction. So inlet and outlet directions. So what the app does with these inputs, it does all the CFD processes that I explained in the previous slides: the CAD cleaner, fluid volume extraction, mesh generation, and the CFD simulations. So all these things are performed autonomously in the background. Now, once the process is completed, what the app provides as an output to the user. So first and foremost is the CV, KV, and CDT curves and head loss coefficient curves. So those are quantitative data that you get, and it also provides 3D results for advanced analysis. So where you can spend time, analyze your design, and identify the scope for improving the changes in the design so that the CV can be improved, flow capacity can be improved. Okay, so and the last output is the report, technical report, which is ready to submit to your end client, as good as the flow loop test reports. It contains all the necessary data required for a technical report, CFD simulations. So I'll show you the demo. Okay, so as I said, this is a web application. So this is the demo. Here's the demo. So as I said, this is a web application. So it opens in the browser. So you can visit simulationhub.com and log into the app using your account credentials. And then this is the dashboard of the app, and where you can create new simulations. Start with the description about the simulation created. So the first step is to upload your CAD model. This is the input CAD model required. So the app supports CAD models in different formats: IPT, STEP, IGS, XT. So all the formats. So the geometry is loaded, CAD model is loaded, and you can view it in the viewer. And now you can specify certain informations about the valve, like what is the valve function? Is it a control or on-off valve? What is the motion type? Is it rotation? Ours is a triple offset butterfly valve, so it's a rotation valve. And what is the type of valve? And what is the trim type? So diameter of the valve, pipe schedule, and roughness of valve and pipe. So these informations are fed. So these information goes into the app. So the next step is to provide or select the moving parts, moving components. There are tools that are available in the app which helps you to pick or select those moving components or trim. Then once that is done, then you have to provide a rotational axis of rotation or axis of travel in global case. Now it is rotation. So then you specify the minimum and like minimum and full opening position and the number of intermediate steps for which you want to simulate the CV. So here I'm entering like 20 and 90 and 8 steps. So it is like every 10 degrees it forms a simulation. So you can view the preview and check the direction of rotation. So if you want it to be rotated anti-clockwise or clockwise, you can use the reverse direction things. So such options are available. So moving on to the next step, which is providing the flow direction. So by selecting the inlet pipe connection and the outlet pipe connection. Okay, so this way the app identifies the flow direction. Now you're all set for submitting the simulation. So once you submit the simulation, so it will ask for the credits. We submitted 8 openings, so 8 credits, and the simulation is started. So all this progress and steps, fluid volume status, mesh status, and the salt status. So all these things you can monitor on your local machine, but the computations are happening in the cloud platform. Okay, so all the angle of openings are running parallelly. It's not in queue. So every opening has a dedicated cloud computing machines, the cluster machines started, and they are running parallelly. So once it is complete, the results are completed, the simulations are completed, you will receive a mail notification. So meanwhile, you can close and look at the other design, or you start a simulation for another design. So it could be anything. You can. It's completely distinguished. So simulations are started, and you can. Once you get the email notification that simulations are completed, you can continue from here. So you can view the results in the viewer or a browser. So these are the quantitative CV table, detailed gross and net CV values. You can view it in the form of curves as well as the table quantitative. You can also export these data in a CSV format for detailed analysis. So now we are entering the qualitative data analysis. So qualitative results such as flow lines, which will help you to identify which are the flow recirculation zones, where the vortices are formed. So these kind of information can be viewed and analyzed from this 3D results, qualitative results. So moving on to the contours or slices, cut sections, which will help you to plot with colors. So I'll tell you how to interpret the results. Maybe the blue color indicates the low velocity or flow separation zones, which is consuming or eating your power. So these are the regions you need to target as a designer to reduce this, particularly behind the shaft. Maybe can provide a fillet or something to avoid this flow separations to improve the flow capacity of CV. So these are the blue regions which you need to target, flow circulation regions. And this is velocity contours. So the same cut sections can be viewed with the pressure. So when you plot pressure, that gives a different information. So the blue region again here shows the minimum pressure, the low pressure region. So this is kind of more helps you identify which regions are more prone to cavitation. Okay, so this way it helps you to analyze the results in much detail. So these are quantitative and qualitative data. Now the user can view the report, the auto-generated report. So where it has all the informations, the CV table, the curves, CDD tables, the detailed explanation about the CFD process followed, and all the color cut sections necessary cut sections for all the openings, pressure and velocity, everything is included in the report. So this is very consolidated report, which you can readily hand it over to the intern. So that's about the demo. Okay. Now it's good to see what is happening in front of the screen, right? It's wonderful. Maybe it will be more exciting to you to understand what is happening behind the scenes, how it is being done. That will, build some trust. Everything is happening automatically. So what's happening behind the scenes? That is, wonderful. What is making this magic? So we have developed autonomous algorithm which intelligently identifies the gaps and sharp corners which need some approximations, and some gaps needs to be closed, some gaps needs to be preserved. So the algorithm identifies it automatically and does the cat cleanup and fluid volume extraction autonomously. So the next step is mesh generation. So as I mentioned, physics-based mesh generation or mesh refinement is required. So here you can see different level of mesh refinement. So this is one level and the next level and the next level near the surface. So wherever there is a flow separation expected, the mesh refinement is automated. So upstream it is less and the downstream it is more. And there are boundary layers, prism layers generated to capture the boundary layer physics. So all these things are done autonomously by the algorithm. And the solution is converged, whether the solution is converged or not, the app monitors this automatically and ensures whatever the data at the end you receive is well converged. Okay. So from here, it will be appropriate to change the phrase. It is no more behind the scenes, it's up in the cloud. So everything is happening in the cloud. So it starts with user submitting the valve design and goes into AVC. So for a single valve and single opening, what happens is the app starts a dedicated 36-core EC2 machine in AWS Amazon Cloud platform, where this simulation of APIs are called cat cleanup, meshing, and solve. Everything is used, and the results, once the simulation is completed on the cloud, the results are available in the viewer, and the CV and CDT data is calculated. So this is for one valve and one opening. The same thing is happening for the complete range of travel for all openings for the same valve. So the app starts dedicated 36-core machine for each openings. So everything runs parallelly at the end. Once the simulation is completed, all the simulation results are available at the same time, and the CV curve is plotted, and the reports are generated, and 3D results are available for viewing. So it doesn't end there. The thing is, let's say you have multiple designs to test. Okay, you're curious to know how each design behaves. So you can start the runs parallelly for all the design options you have for the valve. So all these simulations seamlessly, parallelly runs, and the CV curves are available for comparison at the end of the simulation. So everything is happening in 1 or 2 hours of period. Okay. So again, another advantage over here is being in cloud and web application is your team might be sitting in different geographies and working on different new product developments. Something could be, your company might be working on a glow valve or a ball valve or a butterfly valve at the same time. So different teams can submit their simulations and get the CV results and the report generated at the same time parallelly without any queue or any conditions. So good is it, isn't it? So now I think we'll be able to appreciate and compare and appreciate what is the value that simulation adds to the whole valve design community. So in a conventional CFD method, for a designer to reach this result stage, he has to rely on a simulation expert, and the simulation expert in turn does all the CFD process manually, and then he's limited by his available or accessible, whatever is accessible to him, as an in-house resources, computations. And this takes sometimes like weeks, days or 2 weeks. And whereas on the other hand, simulation CFD, which we saw, so uses the simulation of autonomous process. It does all the CFD process autonomously, and because of the cloud computing, depending on the load, the machines can be expanded, or depending on the load, you can make use of leverage the cloud computing facility. And in the results, because of this autonomous and cloud computation, the results are available in hours, and you're ready with the results. So good comparison. And okay, so now everything happens autonomously. That's okay, but how do I trust the results? Are they really reliable, right? So that question is still needs to be answered. Okay, so what we have done is we have performed validation studies, number of validation studies, some validation studies partnering with the clients as well in their with their data. So I'll start sharing those. So here you're seeing DN 1800 valve, which is very large size valve, for which the CV curve of is compared, the experimental and AVC. It follows a very closely following the experimental curve. And here you can see these are validation studies performed in the real in client data. So they have valve designs for which they have performed a flow loop test, and the lab report is available, for which we performed the simulation, and we found it to be more than 90% accurate with the experimental results. So this we do it as a trust building activity. So even if you have any of your valves for which the CAD model and this flow loop test data is available, so we can perform this simulations and provide you with the results compared. So this is another interesting case we did for a DN40 full port ball valve, where we were able to reach up to 98% accuracy with the experimental results. And this is one recent study which we did for a Russian client, where we compared globe valve with their data, and then we found it like with only within 5% deviation for the higher angle of focus. So it was like 95 plus accuracy range. Okay, here's an interesting success story. So there was a client who was facing a situation where they had a target CV of they have promised their end client to have a CV of 1 lakh, 1,20,000. So now they performed a base design, and they realized their CV is in the range of it's not there yet. So what they did is they approached us, and our support engineer teamed up with their designers, and worked out few design changes, and we need to take care of the strength regulations as well, right? Like there are some design standards which which acts as a constraint to the flow or design changes. Like, so we worked out few design options, and then we were able to achieve the required target CV within a time span of 3 hours and approximate cost of $80. So design optimization problem is done. So that was a very good success story with the client. Okay, so here I'm sharing new features which we have added recently, with which we are able to support very complex geometries like anti-cavity trim kind of things. So where user can either he has a choice to leave with the default meshing algorithm, or if he wants to override and provide his refinement, add additional refinement, the user can select the particular part and apply a refinement whatever is appropriate. Okay, so with which this kind of detailed results simulations are now possible with AVC. And this is what is happening behind the scene. So, these mesh refinements can be applied. So, which enables us to capture the trim gaps and holes clearly. Okay. So, okay, moving on to few consultancy projects which we have been handling for. So this is for Sierra valves. We did a nozzle check valve, and they have been pioneer in adapting to the CFD technology, and they have been leveraging this technology along with AVC and simulationHub team, and they are going ahead with a very latest designs and wonderful designs. They are testing the uh, design space completely with this CFD simulation. So here's the nozzle check valve for which zeta and KV curve is compared. And we are also doing some R&D work, which is in the incipient cavitation index or liquid recovery factor (FL). So we were able to see some very good positive success in the simple cavitation or like orifice geometries. So we compared it with the lab results. So it is more than 95% accurate. So now we are trying to extend this FL and incipient cavitation to the real valve geometries as well. So that is in progress, and soon you'll be hearing something from us, something exciting from us. So even if you have any such project requirements other than CVKV, you can check with us. We'll be more than happy to discuss them with you and work out some possible solutions. Okay, so I'm glad and excited to make a big announcement through this webinar platform. So this announcement is exclusive for the valve manufacturers. Now we have unlimited valve simulations for yearly subscriptions. So the users can perform, any number of valves, any number of CFD simulations for a $5,000 per year subscription. So the complete support and everything is available. So multiple users can log in, and account maintenance and everything is included in the subscription. So, and now you can start with a 15-day trial and try out our apps. So we provide sufficient credits to try out two valve simulations. So you can try that out. Can right away log in and register for free trial in our website www.simulationhub.com. So we also, as I mentioned, we are also open to conduct validation studies for your valve data. So if you have any lab tested valve data as a trust building activity, so we can start with that. So feel free to reach out to us. So if you have any other requirement, custom requirement, we can accommodate that as well. So we have different subscription plan for, we can customize the subscription according to your requirement. So feel free to connect with us. So with that, we have reached the end of the session. Manish.
Yes. So thank you, Praveen. That was fantastic presentation. Autonomous Valve CFD will definitely empower valve designers by freeing them to expeditiously create innovative designs and effective solutions, valve solutions. So yeah, so now we'll go ahead and take some questions now. So participants, if you have any questions, just feel free to drop them in the chat box. So meanwhile, we have received some of the questions. So first one is, do you support globe valve?
Yes. We do support globe valve. Different type of global angle global and S-type global. So that is supported in the app. So what I've demonstrated is a butterfly valve. Similarly, we can you can visit our simulation gallery as well. Manish can share the link for the gallery for all the participants so they can view the global results and experience the result viewing stage themselves. We do support global valves.
Yes. So the next is, what is the dependency of valve size on simulation time?
Oh, okay. I'd say it's not considerable. It's not considerable depending on the valve size, because see, you'll the simulation time might vary because of the valve size, but it's not considerable. Okay. So the algorithm expands and based on the requirement. So all your valve simulations will take somewhere in the range of 1 to 2 hours. So for some valve types, in fact, not valve size, for some valve types, you might observe some longer durations. But overall, it's the average time that it takes. So it doesn't have much impact on the simulation time.
So, what is the security of CAD model, which the designer uploads?
Thanks for asking this question. Let me see if I have that. Yes. So, Rohit, would you like to pitch in? Rohit is our software manager, and
yes. So regarding wall security, when wall designer upload a CAD model into our system, it's anonymous to us. So we cannot get the detail of his project. We cannot get access of his geometry until he provides or grant access. So let's say if simulation fails, so he can grant access to us, and our support engineer then can take a look at the simulation results, and if any suggestions related to modifying the wall geometry, he can provide those suggestions. But until and unless any wall designer or any user grant us the permission, it is not accessible to us. So it is under the AWS security layer and encrypted by various security standard provided by AWS. So you can stay relaxed for your CAD model.
Thanks, Rohit, for the.
So we have one question. What is the background of CFD code? I mean, what is the code used in the background for CFD?
Oh, okay. So we are using OpenFOAM solvers, which is now have become a common practice, and that is verified and validated, tested codes. And on top of that, we are also validating those results. So OpenFOAM is the technology, and which we are using in the background solvers for CFD.
Can actual pressure values be given before starting the simulation?
Yes. Before, can you complete the question?
Yeah, can actual pressure values be given?
Okay.
Like an input, I guess.
As an input. Oh, okay. It can be given. Right now, it's not. It cannot be done in the app. But if you have a specific requirement, you can connect with our support team, and they can make those arrangements. We can do some tinkering in the code and then make it available for you. But if there is any specific requirement, you can connect with Manish support team, and then we can address it. We can work on it. It's possible.
Sure. All right. I guess one last question. Can we use data generated from software to size valve?
Okay. Yes, you can. But see, what you can do is you can generate this complete CV table. Okay. So you can use this as a base to size your valve. So if you know your operating pressure or required capacity, so you can match it with the complete CV table, and then you can do it. And there are some other software tools specifically available for sizing. There you can, where this CV curves or plots data goes as an input to those softwares. So that way, yes, it can be done. Not straight away directly from the app. That's a manual process. You'll have to do it separately with the provided data.
All right. I guess that's okay. One more question. How can we use trial version?
Okay. So you can log into Manish will send after this webinar. Manish will send email to explaining having a detailed procedure to for trial subscription, and there you can you don't need any special things. So you just have to follow the procedure. You can log in directly to the website and register for trial subscription, fill out few details, get account credentials, and straight away start using it. So it's possible. And there are some tutorials or how-to videos to assist you as well. So if you get stuck somewhere, feel free to contact support. There is a chat and provision available. So there, or you can directly write us to on support at simulationHub.
Right. Even you can schedule a demo at
Yes,
whichever time you're first.
we'll be free. Like we'll be happy to connect with you and have detailed interaction to understand your domain and your products and how we can cater your needs through our products.
Right. Okay. So I guess that was it.
Okay.
All right. So, okay then. Thank you everyone for attending this webinar. And I hope this webinar was knowledgeable and provided you some insights on how Autonomous Valve CFD application can help you accelerate your valve design process. As I mentioned earlier, the recording of this webinar will be available on our website and our YouTube channel. So you will also get the link of the same in your email. So yeah, thank you again for joining us, and we hope to see you at our next webinar.